Welcome to this explainer of applied performance tuning, brought to you by Forge College. So last time, we explored the foundational theory of execution optimization on Solana. We talked about contention, we built a pretty solid mental model. But today we're taking that theory and actually putting it to work. We are figuring out exactly where to put the wrench. We're transitioning from those high-level theoretical concepts straight into the concrete, applied performance tuning of Solana's Sealevel runtime.
We have all been there, right? You deploy your program, you run a test, and you're just staring at the screen asking yourself, why on earth is my transaction so slow? And let's be completely honest here. The classic developer instinct is to immediately blame the runtime scheduler or maybe resort to the time-honored tradition of guess-and-check coding. You know the drill. Change a random line, recompile, cross your fingers, and just hope the latency drops. But today, we're bridging the gap from our previous lesson. We are leaving the guesswork entirely behind and learning how to actually diagnose the system like a pro.
To pull that off, we have to follow the absolute golden rule of performance tuning. Measure, isolate, change, and then measure again. Seriously, I want you to start treating your program like a patient and your performance metrics as vital signs. I mean, you wouldn't want a doctor performing surgery without checking your pulse first, right? The exact same logic applies to your code. What you record fundamentally determines which changes are actually worth implementing.
Okay, let's dive into this blueprint. We're going to cover moving from theory to practice, reading the bottleneck signals, some real-world tuning scenarios, our 5-step workflow, and finally, preparing for load balancing.
First up, moving from theory to practice.
As we learned previously, identifying contention sources and separating pure compute from IIO-bound work is absolutely crucial. But honestly, having a mental model just isn't enough without a repeatable measurement approach. You don't locate faulty instruction streams by randomly whacking your code with a metaphorical wrench. You do it through methodical, targeted profiling. Think of it like this. It's the difference between guessing where a leak is in a massive plumbing system versus using a precision pressure gauge to find the exact faulty valve.
Which brings us right into Section 2, reading the bottleneck signals.
When you're profiling, you are essentially hunting for signals. But remember, metrics are just symptoms. They tell you where to look, not necessarily what you need to change. Treat them as hypotheses. The first major signal is compute units, which represents CPU equivalent work. If you see a massive spike here, it usually indicates some sort of algorithmic inefficiency. Like say, humorously recomputing a massive Merkle proof inside a loop instead of just doing it once outside the loop. A classic algorithmic smell for sure.
Our second signal is account lock contention. When a bunch of transactions queue up for the exact same address, the Sealevel scheduler basically has no choice but to serialize them. It forces them into a single file line. And let me tell you, this absolutely kills your parallel throughput. It shows up as increased latency, and it basically means your program is fighting itself for access to shared state.
The third signal to watch for is heap or memory pressure. This is all about the amount and frequency of allocations happening during execution. Long-running allocations or unnecessary data cloning, that can severely slow down your instruction throughput and literally ruin your cache behavior. It almost always points straight to inefficient data layouts in your code, and this brilliantly illustrates how every single metric maps directly to a specific underlying mechanism, which in turn requires specific instrumentation to actually diagnose. For compute units, you rely on runtime meters. For account locks, you're digging into trace logs for wait times. Treating a high metric as the direct root cause is a total rookie mistake. Instead, you want to use these tools to intelligently narrow down your search space.
All right, Section 3. Let's look at some real-world tuning scenarios. Because in the real world, you're usually going to face two recurring nightmares: unexpected latency spiking at scale or a complete failure to grow your throughput. Let's tackle the first one. Imagine you've got a payments program processing batch transfers. Customers are reporting massive slowdowns as concurrency rises. You check the data, and your median compute is actually fine, but your 95th percentile latency has just skyrocketed. Profiling reveals a shared treasury bottleneck, meaning every single transaction is waiting on account locks for one solitary treasury account. The fix here? Shard that treasury into multiple accounts. Partition it by user or region so those transactions can go back to processing in parallel.
Or consider a scenario heavily relying on cross-program invocation, or CPI, chains. You have a top-level transaction that invokes multiple programs, and every single one of them deserializes and then reserializes the exact same account data. Your compute units will be completely through the roof.
Fixing this requires smart transaction composition. You need to consolidate that shared logic so you aren't doing duplicated, wasteful data work across your CPI boundaries.
Next up, Section 4, the 5-step workflow.
So, the crucial point is, to consistently find and fix these kinds of issues, you need a rigorous process. In fact, mastering this strict, repeatable workflow is exactly the kind of optimization mindset we cultivate in our advanced programs at Forge College. It constrains the scope of your changes and forces measurable outcomes. You literally cannot skip these 5 steps if you want to systematically diagnose and cure a slow program. Baseline, perform targeted profiling, form a hypothesis, brainstorm candidate fixes, and prioritize. Let's break them down quickly.
First things first, you must establish the baseline. You select a representative transaction shape and record the exact load conditions. We're talking requests per second, median latency, and the 95th percentile. Then, you use targeted profiling with short-duration micro-benchmarks to isolate those hot paths. You have to know exactly what normal looks like before you even think about changing anything.
Next, based on those traces, you write out a mechanism-level hypothesis. Something like, serialization on the treasury account is causing lock weights. Then you start brainstorming candidate fixes. But here is the absolute most important part. Every single candidate fix must be paired with one specific validation metric. If you suggest sharding the treasury, your metric, to mathematically prove it worked, is reduction in lock wait time. No metric, no fix.
Finally, Section 5, preparing for load balancing.
We prioritize those brainstormed fixes by their estimated impact versus their cost. And this brings us to your final deliverable, which directly sets up the next phase of your engineering work, a crisp profiling checklist and a ranked list of candidates. This is exactly what you take into the lab. Having a crystal clear baseline, a short list of targeted traces, and one single success metric per candidate, that prevents all that noisy, confusing back and forth during your experimentation phase. It keeps you highly disciplined.
Because once you have that checklist in hand, well, the real fun begins. Are you ready to stress test your candidates? In the next phase of your optimization journey, the load balancing experiments, these carefully crafted hypotheses are going to be put to the ultimate test under massive concurrency. You will apply one candidate at a time and measure the true impact under intense stress.
So, I want to leave you with this to ponder today. If you ran a baseline on your current most important Solana program right now, what hidden bottlenecks might be lurking in your code? What silent serialization issues are secretly killing your throughput? To master this subject, dive deeper into Sealevel execution and explore a ton of other advanced Web3 topics. Make sure to visit forge.college. Grab your diagnostic tools, start measuring, and I will see you in the next explainer.